The question that I have is, could you illustrate the vector method of finding moment via an example? In this example, we have a three-dimensional force of 30 Newton is acting at this point, and they have given us the direction angles alpha, beta, and gamma for the force. The question is to find the moment of the force F about the AA axis, which is this. So what is unique about this problem? Well, the axis does not coincide with any of these coordinate axes. The problem is somewhat ill-defined in the sense that they say find the moment about AA axis, but they didn't tell us the direction for the AA axis, right? So let's go ahead and define the direction for the axis ourselves. So I'm going to take this as the direction for the axis. Now we follow the guidelines. First we need to define the starting point and the ending point for the R vector. The guideline says the point O, the starting point, has to be chosen on the axis, right? On the A axis. According to the guidelines, you can choose any point on that axis, but you can see this is the logical choice because we know the coordinates of that point. The end point has to be on the line of action of the force, and therefore this is the logical choice for that, because again that happens to be the origin of the coordinate axis. So here are the coordinates of point O. I have written them in meters. So in the x direction you go 100 millimeter or 0.1 meter in the positive direction to get to point O. The point O is right on the xz plane, therefore the y coordinate is 0. In the z direction we go 50 plus 100, which is 150 millimeter in the negative direction to get to point O. So the z coordinate therefore is minus 0.15 meter. Point A, of course, is the origin of the coordinate system, and therefore the coordinates are 0, 0, 0. Now you construct your R vector between the 2 points like shown over here. You recall this from our chapter on the vector analysis, right? Now let's go ahead and write the force in its component form. We note that what we are given are the direction angles alpha, beta, and gamma, right? With these angles, we can find the unit vector along the force F. Then the vector F equals the magnitude of F multiplied by the unit vector in the direction of the force, right? So here are my calculations. So vector F equals 30, which is 30 Newton, which is the magnitude of the force, multiplied by cosine 60, because alpha is 60, times I plus cosine 60 again, because beta is 60, multiplied by j plus cosine 45, because gamma is 45 degrees, multiplied by k. And we simplify that, and we get this expression for the component form of the force vector F. The next thing we want to find is a unit vector along the axis AA. By looking at the geometry, we realize that axis A is actually parallel to the y-axis, right? We know the unit vector along the y-axis is j, right? And therefore, the unit vector along the a-axis is also j. So UA is simply little j. Now this is exactly why the direction of the axis was important, because remember this is something that was not given, right? So we have chosen this arbitrarily, but if this arrow had been in the other direction, then the unit vector along that axis would have been minus j, right? Also remember, a vector is something that represents the direction of a line. It does not represent the location where the line is coming from, right? So all parallel lines will have the same vector. And therefore, if the unit vector along the y-axis is j, the unit vector along the a-axis is also j. So there are three things we had to find in solving this problem. We had to find the vector representing R, we had to find the vector representing the force F, and we had to find the unit vector along the axis A. Now we got all three of them, so we can go ahead and answer the question, which is to find the moment about the axis A. So here's a summary of the three vectors we need. So earlier we saw there are two methods to find the moment about an axis, right? Method 1, we find the moment about point O, and then we find the dot product between that moment and UA. So that will be the moment about the axis. So let's follow this method first. I will come to method number 2 in a second. So here are my calculations, and we have done this a couple of times. I'll let you follow through. Now this is a special case where we know the unit vector along the a-axis is identical to the unit vector along the y-axis, right? And therefore the moment about the a-axis must be exactly equal to MOY. In other words, the y component of the MO vector, which is 4.37 Newton meter. So we can right away identify the value for the moment about the a-axis to be 4.37 Newton meter. But next time when you do, the UA vector may not coincide with any of the three axes, right? So in that case, you want to follow the general procedure, which is to find the dot product between UA vector and the MO vector, right? So you put that side by side like this, multiply through, and simplify it on the basis that I dot j is 0, j dot j is 1, j dot k is 0, and so on, right? So if you simplify that, we end up with the same number, 4.37 Newton meter for the moment about the a-axis. Our second method is to utilize this direct equation for MA that we talked about before. So here are my calculations which lead to the same number, 4.37 Newton meter for the moment about the a-axis. So what did I do here? Well, I recognized that in the first row I have the components of the UA vector, right? So here I have the x component of the UA vector, which is 0 because we don't have an I term in here. And the y component of the UA vector is 1 because this is 1 times j basically, right? So I have 1 here. And then the z component of the UA vector is 0 because we don't have a k term in this vector. So that is 0 here, right? So that's how I construct my 3 by 3 determinant. And these two rows are basically the same as the one that we had for the expression for the MO vector, right? So going from here to here, in general, we would have had 3 terms involving the 2 by 2 determinants, but this time we recognize that the first term is going to be 0 because we are multiplying the first term by 0 here, right? So 0 multiplied by whatever left over here, and also the third term is going to be 0, and therefore only term that we had to worry about here is the second term, right? If you recall, we start the second term with a negative sign, so the second term is basically minus 1 multiplied by the leftover numbers, which are minus 0.1, 0.15, 15, and 21.21, right? So you go ahead and expand that like we normally do, and we get 4.37 Newton meter for the moment, which is exactly same as what we got by method number 2. So you can see this method is a little easier, all right? So the number of calculations are a little less. So this is all we need to find. In other words, if you just need to find the moment about the a-axis, then this method is a little easier. But if you have to find the moment about other axes like x-axis, y-axis, z-axis, and so on, in addition to finding the moment about a-axis, something like that, the first method will be a little easier. Also note that when we found the MO vector, we had vectors over here, right? We had the unit vector I here, unit vector j here, unit vector k here, and then we ended up with the vector expression for MO. Whereas here, we don't have any vectors. These are all scalars, right? So these are all numbers, right? No vectors in this equation at all. And therefore, we end up with a number, basically a scalar for the moment about the a-axis, the way it should be.